Okay, let's start part 2 of chapter 8. This is going to cover the second page of your lecture notes. In chapter 8, we will take a closer look at metals. We've talked about ionic and covalent bonding, but now we need to take a closer look at metallic bonding. Metals have very specific properties, such as they are malleable, they can be hammered into sheets, they're ductile, they can be pulled into wires, they're good conductors of both heat and electricity. How can we explain this on the microscopic level? We want to take a look at how metallic bonding is different. In an ionic bond, you've got elements with such different electronegativities that one element completely transfers an electron to another, and then you have an attraction between the ions. With covalent bonding, you are filling that outer valence shell and completing octets by sharing electrons. Most of your metals would need a lot of electrons to fill that outer valence shell, and so we see that when we have metals bonded to one another, it looks very different. There's a couple different models, right? We saw different theories of covalent bonding. We have two that we're going to look at for metallic bonding. The first and the most simple, it's just a qualitative model, is called the sea of electrons. This helps us to understand malleability, ductility, and conductivity. The valence electrons are delocalized and move freely throughout the solid. Right, so delocalized. Right, so instead of being shared by two specific atoms, they are free to move around throughout the solid structure. So the delocalized electrons that move freely. That does help us to understand how it can conduct electricity, right, if there is a free flow of electrons. And from here, before we go any further, I want to show you this little video.
Metals, because metals have electrons.
It's just 32
seconds.
if
sea of
you know.
electrons. It means that the electrons don't really belong to a particular atom of the metal sample. They just kind of bounce around and belong to all the atoms in that sample. And that's different than nonmetals. Nonmetals have a little more ownership of their electrons. See all those little flashy lights? Those are the electrons forming the sea of electrons. And because they're mobile, because they don't really belong to any particular element, they can cause all sorts of interesting properties.
And because they're mobile, because they don't really belong to any one particular element, they can cause all sorts of interesting properties.
All right, and so when we think about that sea of electrons, again, that really does help us to understand how it could be conductive, but also think about what that means for its physical properties, right? If we apply a force to a metal, there's not just this one localized bond that might react to that force and break. You are going to push the atoms, right, in the direction of that force, but the electrons that are holding them together are more mobile. They are more flexible. So you can mold and hammer and twist metal without breaking it because those electrons are going to respond and still hold the atoms together even if they are in, a different location. Now, band theory is a quantitative model. It's a little bit more complex and is more quantitative. It's analogous to a molecular orbital theory that you would get into in organic, and it takes into account that you have those atomic orbitals that are going to combine to form new orbitals. So you've been introduced to something like this before when you talked about valence bond theory, but now we're looking at the whole atom of the metal, and when the orbitals come together, they can have constructive overlap or deconstructive overlap, which again we talked about in the last chapter when we talked about sigma and pi bonds. That constructive overlap is called a bonding molecular orbital. If they come together in a deconstructive way, you get an antibonding orbital. And something that is important to know is that however many atomic orbitals are added together, all right, so if there were 2, for instance, you're going to get the same number of molecular orbitals, right? So two atomic orbitals will come together to give you 2 molecular orbitals. Typically, half are lower in energy, which would be bonding. Half would be higher in energy, which would be antibonding. This slide just reiterates what I just said. All right, now the lower energy versus the higher energy. We've already talked about electron configurations quite a bit. We know that electrons prefer to be in the lowest energy orbital allowed. So when we look at band theory, and this is a good graphic for band theory, we're going to start off really small. We think about just a very simple element, lithium, right? Lithium has 1 valence electron, and that valence electron is in the 2s orbital. That orbital has a specific energy. When you have 2 lithium atoms come together, right, so lithium and lithium, right, you are going to get constructive overlap and deconstructive overlap. So you're going to get a bonding orbital and an antibonding orbital, right? One is lower in energy, one is higher in energy. Remember, these are just areas of space figured out mathematically where electron density could be found. Since each valence electron for lithium has 1 electron and an orbital can hold 2 electrons, both of the valence electrons from lithium are going to occupy that lower energy bonding orbital. Now, as we start to add lithium, because we're going to be interested in bulk material here, not just 2 lithium atoms. When you start to add more lithium to the story, right, you're going to increase the number of bonding and antibonding orbitals, right? If we have 4 lithium atoms, right, so 4 lithium atoms, each come with 1 atomic orbital, that's going to lead to 2 bonding and 2 antibonding orbitals, right? You're always going to have the same number of molecular orbitals as you had atomic. As this continues on and even goes in, 3 dimensions, you are going to wind up having this whole band of bonding orbitals, right? So if we just have lithium in both directions, right? Just in number of lithiums, there are going to be the lower energy orbitals and the higher energy orbitals, the bonding orbitals and the antibonding orbitals. All of the electrons are going to be in the bonding orbitals. Okay, so that is kind of the structure or the basis of band theory. Now, the energy levels are very close together for metals, right? Your bonding, or also known as our valence band, and let's get to our picture here. This is, let's see, when we have our bonding and our antibonding, right? This is your valence band, and this is your conduction band here. Your valence band, right, is where all of your valence electrons at ground state live. Now, when we apply energy, for instance, when we apply, an electrical current, when we apply some sort of energy to this and electrons get excited, they can go to an excited state. And for a conductor, for a metal, that next lowest energy level is just right there, right? They're very, very close. So that conduction band is the empty band where the excited electrons can go, right? So the conduction band right, let's do it over here. Sorry, my notes are a little crazy. The empty band where excited valence electrons can move, right? So for metals, the conduction band and the valence band are very close together, right? So conductivity, movement of electrons is really easy. A semiconductor has a band gap, right? The valence electrons, if they're excited, it's not as easy for them to move up into a higher energy orbital. That next higher energy orbital has a space, right? An insulator has an even bigger band gap, right? Essentially making it impossible for electrons to kind of jump around, to move around, right? There's just too much energy difference here for them to overcome that, right? So you have your conductors, no band gap, semiconductors, a small band gap, insulators, a very large band gap. Now, semiconductors, so we're thinking about some of our metalloids, like silicon as a semiconductor, can be improved, right? Oh yeah, we'll talk. Okay, so we'll come to C in just one moment. I left this slide in here for a reason. All right, so if we were thinking about diamonds, right? Diamond is just a network of carbon, and we know that it's an insulator. So if we had to match up which band theory, which molecular orbital kind of system here went with diamond, the correct answer would be C, right? In A, it looks like we have a fairly small band gap. B, this has got to be our metal. There's no band gap. Your valence electron orbitals are right next to your empty conduction orbitals. But C, there's this huge band gap. Diamond is not conductive. The valence electrons that are down here in the valence orbital are not going to be able to make that jump up to the excited state. Now, how can we make semiconductors more useful or more attractive for us? There are ways we can manipulate our semiconductor materials, and that is with doping, right? So I'm going to write as I talk, otherwise I know I tend to talk a bit fast, right? But doping is going to be adding trace amounts, so very, very small amounts of a different element to modify its properties, right? What it's going to do is it's going to affect that band gap, right? So we can make our semiconductors more conductive by adding just a trace amount of a different element. Now, there's two ways to do this. We can do an N-type. We'll come back to donor level here in a moment. An N-type semiconductor has a dopant, right? Or the dopant is just that trace element that you're adding in. An N-type semiconductor is going to have a dopant with more valence electrons. So we'll make that note and then we'll take a look at what that means in just a moment. A P-type semiconductor is going to use a dopant with less valence electrons, right? So more electrons is N-type, or it's more negative. P-type has less valence electrons, or it's more positive. That's how you can keep that straight. All right. N-type semiconductors, let's start there. You're going to have extra valence electrons, meaning that you're going to have more electrons that are slightly higher in energy, right? So if we take something like silicon, right, and silicon has its small band gap here. You have all your valence electrons down here in the bonding orbitals. If we put just a tiny amount of, and what are we using here? Phosphorus. Phosphorus has an additional valence electron to silicon. You are going to still have, since it's mostly silicon, you are going to still have a very similar setup of your bonding orbitals and your anti-bonding conduction band, but you are going to have a few extra electrons. And those electrons are going to be a little bit higher in energy, and they are going to be present in what is known as a donor level, right? Those extra electrons, all right, so your N-type semiconductor is going to have extra electrons in your donor level. That donor level is going to be something that is in the band gap, right? It's going to be closer in energy to the conduction band. And so, conduction band. So with the N-type semiconductor, what you're essentially doing is you're putting some extra electrons up in that gap, in that donor level, so that now it doesn't take near as much work or as much energy to get them excited and moving into that conduction band, right? It's going to make it a more conductive material when you dope silicon with phosphorus. Now, if we take a look at our P-type semiconductor, right, we're putting in something with less electrons. And so we're going to be dealing with something called an acceptor level, right? In the donor level, there are electrons in the band gap. They are from the dopant, right? The acceptor level occurs because now instead of doping with something with more electrons, we're doping something with less electrons. So it's kind of like we're leaving these little positive holes at the top of the valence band, right? It's still mostly silicon. There's a little trace amount of aluminum here. Aluminum has one less electron than silicon. And so there's going to be a little bit of space up at the top of that valence band that's empty, right? So that acceptor level is right above the valence band, and it's empty. It's empty, but it's very, very close in energy. So what we're doing is we're bridging the gap, right? It takes now a less energy to pull those, for electrons to get excited and to move up into that empty acceptor level, right? So let's see. Above the valence band, electrons from your dopant, right, your P-type dopant, can move up more easily, right? There's less of a difference in energy from here to here as compared from here to here, right? So if we have a little bit of aluminum doped into our silicon, this can also make our silicon more conductive. Okay, now one last thing to talk about, on this page and in this little video is going to be something called a p-n junction. So you can really get kind of creative here by putting p-type and n-type semiconductors next to one another. And I think this is better explained with the picture. All right, so you've got your... At the p-n junction, you have p-type next to n-type, right? So you have silicon, for instance, doped with aluminum on one side and doped with phosphorus on the other. So you have a side where there is extra electrons, so there's extra negative charge, and then essentially on the p side you have holes. That's what you're seeing with these plus charges. Remember, this is not... We're not adding protons to this. We just have less electrons. So that acceptor level is kind of like you have these holes where electrons could go. So if we have these p-types and n-types next to one another, we can control the flow of electrons from one side to the other with if we connected a battery. For instance here, right, applied voltage will drive electrons from the n-type to the p-type, right? It's not that the plus charges are moving over. It's that the electrons are moving towards the p-type to fill in those positive holes, right? Essentially leaving positive holes on the other side. Now, if you reverse the voltage, then you will get no electron flow, right? Because you're going to have this plus charge over here. That's going to pull all of your electrons away from that n-type. So a p-n junction is a cool way to implement a switch. And all you have to do is change the direction that the voltage is applied. That's the end of this